Lab 7 had a lot of calculations. Probably is one of the more difficult labs as far as learning new material. So let's look at Lab 7, which was the mole and hydrate lab. So one of the main concepts is what a mole is, right? And a mole is just 6.022 times 10 to the 23 of whatever we're talking about, right? So if you have a mole of dogs, you have 6.022 times 10 to the 23 dogs, right? So it's a number just like dozen. Dozen means 12 of something. And you need to be able to use this mole map, right? So you'll have some kind of problems where you have to go from grams to moles to atoms or something like that, right? And so if we have grams, the only place we can go is moles. If we have moles, we can go to atoms or molecules, but moles kind of sits in the middle. So if you're trying to get across the mole map, you have to kind of go through moles, right? So if we have a problem like this, how many atoms are in 454 grams of gold? From our mole map, we see to go from grams to moles, we divide by the molar mass. So we get that from our periodic table. So here's what gold looks like. Its symbol is AU. Its element number 79, and below it is its molar mass, right? So that's how many grams 1 mole of gold weighs. So if we had 6.022 times 10 to the 23 gold atoms, it would weigh 196.97 grams. And that's going to be our conversion factor, how many grams per mole there are. So what we're going to do is say, well, we have grams, so we have grams. And what we have to do is go to moles first to go across our mole map. And we want atoms, and so once we have moles, we can get all the way across to atoms. So you can see we're going to need 2 conversion factors to complete that problem. We're starting with 454 grams of gold. And we need to get rid of grams, so we need grams of gold on the bottom, and we need moles of gold on top, right? So we need to know how much 1 mole of gold weighs, and that's its molar mass. So we have 196.97 grams on the bottom, and that's our conversion. Now if we look, we're canceling out grams, we're at moles of gold, but we need to go all the way across our mole map to get to atoms. So to go from moles to atoms, we're going to multiply by 6.022 times 10 to the 23rd. So we know that 1 mole of gold contains 6.022 times 10 to the 23rd atoms of gold. So we're going to multiply 454 by 6.022 times 10 to the 23rd and divide by 196.97. And when you do that, you should come up with 1.39 times 10 to the 24th gold atoms. And that number should make sense, right? Because if we had only 6.022 times 10 to the 23rd atoms, it would weigh 196. So we have almost twice that amount. So we have almost twice as many atoms. All right, continuation of Lab 7 mole and hydrate. This next part refers to the actual lab you did. It says you have a 2.50 gram sample of the hydrate magnesium sulfate NH2O, and it was has an unknown degree of hydration. We heated it several times, and what was left was a solid residue weighing 1.22 grams. So remember, hydrate is something that has a water kind of loosely bound to it. So here we have magnesium sulfate with some water molecules loosely bound to it. So that's called the hydrate. When it has the water molecules, once those water molecules have been heated off or removed, then it becomes the anhydrate. Right? So it says how much water was lost. So the sample started out weighing 2.5 grams, and now it weighs 1.22 grams, so the amount of mass that was lost equals the water that was driven off. So if we're doing this problem, then how much water was lost? You just have 2.500 grams minus 1.22 grams, and that would leave you with how much water was lost, which would be 1.28 grams. Right, so we could measure that, and we did with our balances. Now we want to know how many moles of water were lost. So remember from our mole map that we can go from the mass of water, we have 1.28 grams of water, and what we want are moles of water, so we want moles of water on top, and we need grams of water on the bottom. So what we need to do is find that molar mass of water. How much does 1 mole of water weigh? Well, water is made up of 2 hydrogens and 1 oxygen, right? H2O. From our periodic table, each of those hydrogen weighs 1.01 and the oxygen weighs 16.00. So 1 mole of water weighs 18.02 grams per mole. So then we can put in our 18.02 grams here. We're going to divide 1.28 by 18.02, and you should get something around 0.0711 moles of water. All right, so we know how many moles of water were driven off. Now it says how many moles of anhydride are there. So the residue left is the anhydride. It's this magnesium sulfate without the H2O. So it would be this part of that compound, just MgSO4. So we know how much of the MgSO4, we have 1.22 grams of MgSO4 left. And we want moles, so we need to know how much 1 mole of it weighs. And we'd do the same thing that we did for water. We'd add the weight of a magnesium, a sulfur, and 4 oxygen, and we would get a molar mass of about 120.38 grams per mole. And so we divide our 1.22 by our 120.38 and get a number that's about 0.0101 moles of anhydride. So what is the degree of hydration? What we want to do is find the ratio of moles of water to moles of anhydride. Right, because that's going to tell us how many of these waters we have for every magnesium sulfate. So we take our 0.0711, divide it by our 0.010, and that equals approximately 7. So the degree of hydration is 7, and our compound would be MgSO4.7H2O. So that's the degree of hydration, and that's how you would calculate it. All right, so Lab A was about reaction types, and there we learned how to write chemical reactions or equations, to take a description of a chemical reaction and then write out the equation in chemical symbols. So we learned that a solid is abbreviated with an S, a liquid with an L, a gas with a G, and aqueous with an AQ. And remember, aqueous means dissolved in water. So if we had something like a sodium chloride dissolved in water, it would be NaCl, and then we'd put behind it brackets meaning AQ, meaning that the sodium and chlorine is dissolved in the water. We learned about a couple different types of reactions. One was a combination, and that's when we're taking something simple and making a more complex molecule or compound. So here we have copper. Remember, I showed you a video of someone taking a copper piece of foil and heating it up in the Bunsen burner. And in that reaction, copper was being combined with oxygen in the air to make a copper oxide or copper 2 oxide on the surface. So that would be a combination. A decomposition is when we're taking something complex and doing the opposite. We're breaking it into something less complex. So if we took a hydrogen peroxide and it broke down into water and oxygen gas, that would be an example of a decomposition. Then we also talked about single displacement and double displacement reactions, and we'll first look at a single displacement reaction. And in a single displacement reaction, you have one element replacing another element within a compound, and then that other element is displaced or by itself. So if we read a verbal description of this reaction, solid zinc is added to aqueous copper sulfate, and we have to predict the products and balance the equation. So solid zinc we would represent with a Zn and an S for solid, and we added that to aqueous copper 2 sulfate. So copper 2 tells us it's copper with a 2+ charge. If we look at our polyatomic ions, sulfate has a -2 charge, so that would be the compound 1 copper plus 1 sulfate. Now to predict the products, this zinc is by himself. He's going to come and displace this copper. So the zinc will become cation, right? And so zinc forms a 2 plus. This sulfate we said has a 2 minus. So those will go together 1 to 1 when the zinc comes over and combines with the sulfate. So that would be one of our, one of our products there. And if you look at your chart on predicting solubility, this would be an aqueous compound. And now copper is going to be by himself over here. So copper is just going to be elemental copper. So if we look, we have one zinc, one copper, one sulfate. So we have a balanced equation. All right, here we have a double displacement, and that's where the two partners switch. And we'll get to that in a minute. First, we have to put together our reactants, right? And so we have sodium phosphate, which is aqueous, and we've added it to aqueous lead nitrate. So what we have to do is kind of look and say, well, sodium is going to have a +1 charge because it's in group 1. And from our polyatomic ion table, phosphate is PO4 with a -3 charge. So if we put those together and cross multiply, we need 3 sodium for every 1 phosphate. So that would be our sodium phosphate, and we're saying it's aqueous. And what we're adding that to is lead 2 nitrate. So this is telling us our lead has a +2 charge because it's lead 2. If we look at our polyatomic ion table, nitrate has a -1. So we cross multiply, we need 2 of those for every 1 of those. So we have 1 lead, and then we have 2 nitrates. And we're saying that that is aqueous as well, right? So in a double displacement reaction, the two cations exchange positions, right? So this sodium here is going to want to now be with this nitrate, and this lead is going to be with the phosphate, right? So our sodium has a +1. Our NO3 that it's going together has a -1, so those will go together 1 to 1. And one of the other products would be this lead, which has a +2 charges now with this phosphate, who has a -3, and when we cross multiply, we need 2 of those and 3 of those. So we'd have a PB3, PO4, 2. All right, and we're running out of space here. And then you would kind of look on your table of predicting solubility, and you'd see that this phosphate, this lead sulfate, would be a solid, and this would be aqueous. So that's how you would do a double displacement reaction. You're taking the cation here and pairing it with the guy with the negative charge here. So we have a +1 and a -1, and this guy that had a +2 is now with the PO4, which has a 3-. So you're just switching the cations with the other anions.